share my screen. Okay. Uh, by the way, I would point out that I'm no longer in Carthage University, and this is my mistake. I did not mention this. Now I belong to Kirwan University, where I have a teaching position, and I do my research in University of Tunis Al. Okay,
Okay.
and my talk today is based on a joint work with Professor Dorogovtsev, and I would like to start with an example which I discussed in previous talks in this seminar. Uh, it is related with the intersection local time of the Brownian motion. So we consider this functional here. So we have d-dimensional Brownian motion and this integral, and here we have this p epsilon d. It is this Gaussian density, and applied to this increment wt minus ws and minus u. It is a fixed vector from Rd, but different from the origin. Okay, we'll stay away from the origin because the origin makes a lot of problems, really. Of course, why it is important to study this functional, because it is known that p epsilon d is an approximation of, in a weak sense, of the Dirac delta function at the point zero. So when we take formally at least the limit when epsilon tends to zero, we will find the integral over s small than t of the Dirac delta function at the point zero of this increment wt minus ws minus u, or equivalently the Dirac delta function at the point u of wt minus ws. So at the limit, the integral at the limit is intended to describe the time, the s and the t, such that the increment wt minus ws is equal to u. It was proved that this functional has a limit, an L2 limit, when epsilon tends to zero, if and only if the dimension is less or equal than 3. Moreover, this limit, denoted by phi 0, has an E2 expansion. It's a series of multiple E2 integrals. It is given explicitly here, and the multiple E2 integrals appear in these Hermite polynomials from this expression. Okay, now what happens if the dimension is greater or equal than 4? We still can have a limit, but of course it is not a square integrable random variable. It was proved that phi epsilon of w has also a limit, but in a generalized sense, precisely in a Sobolev space D2 gamma, where this differentiability gamma index, differentiability index gamma is smaller than 4 minus d over 2. Okay, let me recall briefly what are these Sobolev spaces. For each real number alpha, this D2 alpha is a completion of the following space, where we have some square integrable random variables, which are a Wiener function measurable with respect to the Wiener sigma field. And of course, each square integrable random variable, which is measurable with respect to the Wiener process, has a need to Wiener expansion, but we will take those with finite number of multiple integrals. And we take the completion with respect to the following norm. It is a small modification of the usual L2 norm. We see here that there are these exponent of these powers of k plus 1 or alpha. Okay, After completion, what we get is a family of spaces for each alpha. We have a space D2 alpha, and if alpha is equal to zero, then this is exactly this L2 space of square integrable linear function. And if we have a positive index alpha, then we have a smaller we have subspaces of this L2 space. And if it is a negative index, then we have larger spaces containing this L2 space. If elements from those spaces with negative index are called generalized function. And in this example, as we said, this limit exists in Sobolev spaces with the gamma is smaller than 4 minus d over 2. Of course, if d is greater or equal than 4, then this gamma is a negative index, and we are speaking about a generalized function. Okay. And we proved that this limit, since it is a generalized function, but it is also positive. And positivity comes from the fact that phi epsilon from W is obviously a positive function. Let me just go back a moment. You see here I have an integral of this Gaussian density from something, so it is obviously positive. And so the limit is a positive generalized linear function, and due to a theorem from Sujita, such kind of generalized linear function can be represented by finite positive measures on the linear space. Using this representation, so we can associate to such function on a finite positive measure mu0 on the linear space, and this representation should be understood in this way. So whenever we test this generalized function by a cylindrical test function of this type, then the result is given by an integral with respect to that measure. Okay. I want also to recall that this positive generalized function, it has an E2 expansion, and it is exactly the same that I showed in dimension less or equal than 3. Let me go back. This is the same E2 expansion, but of course, the convergence should be understood in the sense of D2 gamma. So we have to multiply these multiple integrals by k plus 1 here to the power alpha in order to have a convergent series in L2. Okay. Let me go further. Before I move forward, I want to stop for a moment and recall some results from the literature regarding the intersection local times as generalized functional. It seems that many authors were interested in studying intersection local times as with using Sobolev spaces and generalized functional tools. I would particularly mention the results by Hu and Newellard, who found a condition on the Earth parameter of a d-dimensional fractional Brownian motion under which the renormalized self-intersection local times belongs to some d2 alpha with positive alpha. The dimension, this condition includes the dimension d and the Earth parameter and this alpha, this index alpha, this differentiability index alpha. When the alpha is positive, those spaces can serve to describe the regularity of those functional. Precisely, D21, for example, contains stochastically differentiable square integrable random variable. D22 contains square integrable random variable which are twice differentiable, and so And in a series of papers, also, Alexei Rodenko found several equivalent conditions under which the intersection local time with renormalization or without renormalization of Gaussian random fields is an element of a Sobolev space D2 alpha. And here there is no restriction of this on this alpha. And of course, these are more general results than those obtained by Hu and Muellart, because he also mm, considered general family of Gaussian random fields. And recently, we studied this intersection local time of the Brownian motion in dimension greater or equal than 4. As I said, since it is a positive generalized band function, so we studied it through the associated measure. And we proved the partial results of a large deviation principle, and we found some new asymptotics. Okay, I assume my responsibility. I say new because as far as we checked the literature, we did not find similar results. Okay, let me go back now to this example of uh, this positive general, this intersection local time of the Brownian motion, and I would like to make a reformulation of those results, of those convergence results, but in terms of measures. So here I denote by mu this the Wiener measure on the Wiener space, and this function of phi epsilon, I will consider it as a function on the space of trajectories on the Wiener space. The previous example can be written in a different way. So, as I said, in dimension less or equal than 3, we have the convergence phi epsilon to phi 0, uh, but phi 0 is a square integrable random variable. From that point, we can deduce that phi epsilon, that the measure with density phi epsilon with respect to mu weakly converges to the measure with density phi 0 with respect to mu. And in dimension greater or equal than 4, it was proved that phi epsilon converges in T2 alpha for specific values of alpha to a generalized function, positive generalized function phi 0. And this positive generalized function is associated to some measure mu 0. And we can deduce that we have a weak convergence of these measures to mu 0. So in all cases, we have some weak convergence of these measures to some final measure. But in these cases here, we have this limiting measure. It has a density, has a square integrable density, and in this case, it is associated to some positive generalized function. Moreover, in all these cases, we have an E2 expansion of this limit with respect to this measure. We have an E2 expansion, so it is with respect to the Wiener measure. And it happens that there is a notion that covers these cases together. It covers the case of measures with square integrable density. It covers the case of measures which are associated to positive generalized functional, and it guarantees the existence of an orthogonal polynomial decomposition. This notion is called by finite absolute continuity, and it was introduced by Professor Dorogobtsev in 2000, and I would like to introduce this concept. So, as a preparation for that, we consider a real separable Banach space with its Borel sigma field and a probability measure on it, which we call mu here. and we suppose that it has weak moments of any order, and that polynomials are dense in this L2 space of B functional with respect to this measure mu. So what is the definition of finite absolute continuity? So we already have this probability measure mu. So if we consider another finite positive measure on the same Banach space B, which also has finite with moments of any order, then we say that it is finitely absolutely continuous with respect to mu if, and we will denote this fact by this notation. It's slightly different from absolute continuity. So, and if for any integer n, there exists a constant that only depends on n, such that for any polynomial p with degree at most n, we have the following inequality. So from one side, we have an integral over b of this polynomial with respect to the measure nu, and from the other side, we have the L2 norm of this polynomial p with respect to the measure mu. And the constant depends only on n, which is the degree of p. Of course, when it is called finite absolute continuity, so probably it has some relation with absolute continuity, and it is true since if nu has a density with respect to mu, then we would have here some functional, let's phi multiplied by mu, and then it is enough to apply Cauchy-Schwarz inequality in order to obtain this, but provided that the density is square integrable. And in that case, this constant Cn will be just the L2 norm of the density with respect to mu, and it does not depend on n at all. And it happens that that's the first example of finite absolutely continuous measures. We have much more than that. We have the following equivalence, that nu is finitely absolutely continuous with respect to mu, and the sequence of constant Cn can be chosen to be bounded if and only if nu is absolutely continuous with respect to mu and the density is square integrable with respect to mu. Okay. Another example is whenever we consider a positive generalized Wiener function and the measure which is associated to such positive generalized Wiener function on the Wiener space, then that measure is always finitely absolutely continuous with respect to the Wiener measure. Of course, we already have an example of such kind of measures when we discussed the Brownian motion in the intersection local time Brownian motion in dimension greater or equal than. And by the way, in this example, this measure nu is in general singular with respect to the Wiener measure. But still, it is finitely absolutely continuous. So this notion of finite absolute continuity covers some cases of absolute continuity and some cases of singularity of measures. Okay. Even we can add a little bit more to this result. We can consider any positive generalized function from a Gaussian measure. I mean, we can replace the Wiener measure by any Gaussian measure. We still have similar
الو
results.
عسلامة. الو
Hello?
عسلامة،
Sorry,
مرحبا.
Sorry, please mute your microphone.
مرحبا.
Yeah.
صباحي صار.
Okay, good. Now let's continue.
Okay, okay. This is Suhail. I thought he is speaking to me in
Oh,
Arabic.
he wanted to call you, yeah?
Maybe.
Very good. Okay,
Okay.
let's continue.
I have a small question. So in the first example, polynomials must be dense, yes, in L2.
Here, yes, by the way, that, yes, I always assume that polynomial are dense.
Okay, okay. Mhm.
Okay. Also, I want to point out that this concept of finite absolute continuity is much more appropriate in infinite dimensional spaces. Precisely, suppose that B is finite dimensional, then, of course, if we fix n, then the set of polynomials with a degree less or equal than n on B is finite dimensional. And this is a linear form on P, and any linear form in a finite dimensional space is continuous. If the measure mu can serve to define a norm on P, then on the set of polynomials on B, then this is an immediate consequence of continuity of linear forms on finite dimensional spaces. So it seems that this notion is much more appropriate to infinite dimensional spaces. Okay, let me go further. And with here, there is another property of this that comes out from finite absolute continuity, and it gives a possibility to have some kind of chaotic expansion of, let's say, one measure with respect to the other measure. Precisely, if nu is finitely absolutely continuous with respect to mu, then we can find the sequence of mu orthogonal polynomials an such that for any polynomial p defined on B, we have the following inequality. Okay. So this is like the equivalent of the E2-Wiener expansion in some way. Okay. Now let me go back to this starting example of this intersection local time. As we said, we have this functional which uh, converges weakly to a positive generalized Wiener functional uh, or to a square integrable random variable. Of course, even square integrable random variables can be considered as positive generalized Wiener function. Now, let us make the following question. Can we take another process instead of the Wiener process and still have similar results? I mean, if we put x of t instead of w of t and keep the same functional, do we have a generalized functional from the process x itself? In another way, does the family of measures phi epsilon nu, where nu is now the measure, the distribution of x, does this family of measures converge weakly to a measure which is finitely absolutely continuous with respect to the measure nu? Or does this family of function phi epsilon converge to a positive generalized function from x? If it happens that this is true, then for a large family of measures nu, then we call this family of functional f phi epsilon to be universal. I mean, we can change the measure, we can change the process, but keep the functional itself, and still we have the same result at the end. It means that at the end we have some functional which is a positive generalized functional from the process uh, itself. in order to answer this question, we introduce what we call uniform finite absolute continuity. And here I will present what is uniform finite absolute continuity on Hilbert spaces, and then we will see how it is expressed in the Wiener space. Okay. If we consider a Hilbert is separable Hilbert space and the centered probability measure on it, which has finite strong moments of any order, and we consider a family of finite positive measures mu epsilon and h satisfying the following condition. Of course, in this our examples here, in my question, this will be mu epsilon. Okay. But here we take the problem in more general. So we take a family of mu epsilon of finite positive measures, and we impose that they all are have finite weak moments, and they are all finitely absolutely continuous with respect to the measure mu. Of course, this will be obvious if mu epsilon is of the form phi epsilon multiplied by mu with a square integrable phi epsilon. But now uniformity is here. Uniformity is with respect to epsilon. We want, of course, when mu epsilon is finitely absolutely continuous with respect to mu, then for each n we will find the sequence of constants c and epsilon. But we want them to be for fixed, and we want them to be bounded with respect to epsilon. Then, under this condition, the family mu epsilon is weakly compact. We will see in some later that we can have a convergent family of measures. This family can be convergent and under an additional condition. And this theorem here is based, the proof is based on weak compactness of measures in a Hilbert space, on separable Hilbert space. And the theorem after considers the case of the specific case of the Wiener space. If we have a centered probability measure on the Wiener space with finite weak moments of any order, and we consider a family of positive finite measures on B, satisfies the same three conditions previously cited. And we assume also that we have the following property. Of course, if this measure mu is the distribution of some process x, then this property means that we have that expectation of xt2 minus xt1 in norm is less or equal than some constant multiplied by t2 minus t1 to some power gamma. And this can be checked for several processes. So now under this condition, the family again of mu epsilon is weakly compact. And so this is uniform finite absolute continuity on the Wiener space. And in both theorems, in separable Hilbert space or on the Wiener space, the uniform finite absolute continuity it can guarantee the weak compactness of this family of measures and the all possible limits when epsilon tends to 0 are also finitely absolutely continuous. And that's what we want from the question that arises when we want to change the Brownian motion by some other process. the following theorem gives us a condition in order to have one unique limit of those measures. So here we take B as a separable Hilbert space or the Wiener space, and consider a family of phi epsilon of positive bounded measurable function on B. So our measures here, mu epsilon, are given in this. And suppose that mu and this family of measures satisfy the condition of uniform finite absolute continuity as mentioned in the last theorems. And in addition, we suppose that for any finite dimensional polynomial P, the following integral of P with respect to mu epsilon has a limit. Then we can prove that phi epsilon weakly converges to a positive generalized function from measure mu. And this family of measures is convergent, and that's much more better, of course, than weak compactness. Next, I prepared some examples in order to apply these results. And of course, we already have the example of Brownian motion that is discussed in the beginning. It also can be checked through uniform finite absolute continuity. But here I will take as a first example some more general example than the Brownian motion. And of course, here the Brownian motion will be a particular case. So we consider the d-dimensional Brownian motion, and we consider some fixed measurable function which are bounded from below and from above in absolute value. And we define the following Gaussian process. All the coordinates are of the same form, but with different here function, and of course with different coordinates of the Brownian motion. So we get independent coordinates when we get all the coordinates as in this martingale form. It's not so complicated process. But okay, as a beginning, I will show you then that I just wanted this example in order to see what we need to generalize for more general processes. We can check that the distribution, of course, of this process is a centered Gaussian measure on the Wiener space. And then we will consider the same function as in the beginning. Okay? Here, delta k just means that we take t1 less than t2 less than tk. So there is no just one increment, but here we use k minus 1 increments of this process. This is intended to, of course, if we think about the limit when epsilon tends to 0, then we will get the integral over delta k of a product of Dirac delta function at the point u of these increments. And this is also intended to describe the time that the increments of this process are equal to u. A certain number, k minus 1 increments, successive increments are equal to u. So we can apply the last two theorems, the uniform finite absolute continuity on the Wiener space, and the last theorem, which allows us to say that phi epsilon weakly converges when epsilon tends to 0 to a positive generalized function from X. This means that we can define this intersection local time of this process X by this formula, by this form here, and it exists and can be considered as a positive generalized function from X itself. I want to show you the proof, but I will concentrate on the main steps. Of course, we have to check the assumption of uniform finite absolute continuity. But okay, let me just come back to those assumption. We need those measures mu epsilon to have finite weak moments of any order. But in our case, mu epsilon is phi epsilon multiplied by mu, where mu is the distribution, the probability measure associated to the process X. This is a Gaussian measure, and this is a bounded functional. Gaussian measures have finite strong moments of any order, and so this consequently mu epsilon also have even strong moments of any order. So this is checked. And now about finite absolute continuity of mu epsilon with respect to mu, since it has a square integrable density, then it is finitely absolutely continuous. So we concentrate on this the third criterion here, and we want to check that those constants that arise in the finite absolute continuity are can be for fixed and they are bounded with respect to epsilon. That's what we do. So we'll come back to the definition of finite absolute continuity. We have to check that absolute value of the integral of a polynomial of degree n integrated with respect to the measure mu epsilon. This is the measure mu epsilon. It should be less or equal than, we have to check that this is less or equal than some constant Cn and multiplied by the L2 norm, course, of Pn with mu, with respect to mu, integrated with respect to mu. Of course, we'll check that those Cn epsilon can be bounded by a constant that depends no more on epsilon. One can think, of course, to begin with, to apply Cauchy-Schwarz inequality here, but then we will find some constant which depends on epsilon, which is exactly the L2 norm of phi epsilon with respect to mu, and this will give rise to some very complicated integrals. So we think that if we go through this way, it will be much easier, at least. So we can write this. Of course, mu is the distribution of x. So this is exactly the absolute value of expectation of phi epsilon x multiplied by Pn of x, and then phi epsilon of x is the integral of a delta k of these products of these Gaussian densities of these increments, and Pn of x is a polynomial from x. Introducing the expectation, then we just need to replace Pn of x by the conditional expectation of Pn of x with respect to this all these increments. When making a conditional expectation of such polynomial with respect to this Gaussian random vector, we'll find again another polynomial from this Gaussian random vector and with the same degree, or not more than the degree n. And now this integral in absolute value is less or equal. Just we write here the density. We use the density of this vector C of t. It happens that it has a density. Since its covariance matrix can be written explicitly, it is invertible. And we have this kind of integral. And then we make use of the following lemma, where it says that any polynomial of several variables of degree less or equal than m multiplied by this Gaussian density is always bounded from above by a constant that depends only on this degree m, and multiplied by the norm of this polynomial in the L2 space square integrable random function with respect to this dash p gamma and then multiplied by p2 gamma. So if we use this, then we can replace all this by some constant and this constant here, and we replace it by p2 gamma. Of course, we apply this for this polynomial Qn, and it happens that the norm of Qn in L2 with respect to the density p gamma is less or equal than by using the properties of conditional expectation, it is less or equal than this L2 norm of Pn of x, which is exactly what we want to make appear. And then we plug these inequalities in the integral here, and we will find that we have some integral of f epsilon u here from x, p2 gamma of x, and this f epsilon u is just some Gaussian densities, and we can use the convolution property of Gaussian densities and apply a dominated convergence theorem here, and we can make find a limit which does not depend on epsilon anymore. Moreover, so this shows that we have the finite absolute continuity with a constant Cn and multiplied by a constant that does not depend neither on n nor on epsilon. And we have this term, this square, the L2 norm of Pn with respect to mu, or the L2 norm of Pn of x. So we have exactly the uniform finite absolute continuity. Moreover, we can so we have the weak compactness of this family of measures phi epsilon mu, and in fact we can check that the last theorem is also true here. It means that we can remove the absolute value, and we can check that this integral converges when epsilon tends to 0 to a finite limit. We can remove the absolute value, and we do the calculation again. We can check that we have a finite limit of this kind of integrals. So we can apply the theorems, and we can say that our function of phi epsilon converges to a positive generalized function from this process X. And then we can think about generalizing more this example by not taking a process with coordinates here as integral of a function phi j with respect to wj, but we can introduce more general Gaussian integrators. Okay. So we can think about a d-dimensional Gaussian process with the coordinates given by this form, where A is a bounded and invertible linear operator in the Hilbert space L2 of 0, 1, and W1, WD are coordinates of the Brownian motion. These kind of processes are called Gaussian integrators. They are also introduced by Professor Dorkovtsev, and they cover a large family of known Gaussian processes. Here we impose invertibility of this linear operator A in order to have that this random vector here xt2 minus xt1 until xtk minus xtk minus 1, that it has an invertible covariance matrix, and consequently it has a density. So moreover, so this process has a distribution mu, which is a standard Gaussian measure on the Wiener space, and we think about the same function now, and we just need to compare with the previous proof, and it happens that everything work, but we just need this integrability condition of this Gaussian density of this vector that I mentioned, already mentioned. So if we fix u in Rd away from the origin and denote by u tilde this just this same vector repeated k minus 1 times. And if we suppose that A is an invertible bounded linear operator of L2 is 1, and we impose this integrability condition of this density. Of course, this P2 gamma of T depends on T1, T2, Tk. So we impose this integrability condition, then we have a similar result than the previous case. Precisely phi epsilon weakly converges to a positive generalized functional from this process X. The proof is exactly similar. All what we need is to add this condition. As a next step, we are looking for a more general result than this one. So by checking the proofs of this theorem and the previous one, we see that almost what we need is probably the following. So if we take as X an RD valued centered Gaussian process with the following property, this will ensure that we have continuous trajectories, that we have trajectories that live in the Wiener space. We suppose also that this random vector for every T1, Tk, this family of increments have an invertible covariance matrix and consequently a density. And we will take, instead of those family of Gaussian density P epsilon, we will consider a family of positive unbounded function which converts weakly to a measure nu. So previously we were using a family of function which converts to the Dirac delta function at the point u. Now this is more general, and we will define the function as an integral over delta k of f epsilon from the increments. And the integrability condition that I previously used here, which is this integrability condition, now should be replaced by the following. So it is the integral of P2 gamma with respect to nu, and of course with respect to time. This should be fine, and in this under this assumption, we can show that the function of phi epsilon converges weakly to a positive generalized function from the process X itself. Okay, this is all I want to say. Thank you very much for your attention.
Okay, thank you very much for interesting talk. Maybe someone have questions or comments, please.
And I have a question. And if we consider a fractional Brownian motion, it is an integral function of Brownian motion. Can you extend your results to such random processes?
The fractional Brownian motion may probably, I think it can fall in this family of integrators, but provided that the Earth parameter is greater or equal than 1/2. Then it can be considered as an integrated, can be written in this way, and I think that we can apply this machinery and obtain similar results.
And I have another question to your notation. And typically people denote Sobolev space as W capital, and you denote D capital. Does it come from Keller's paper or?
Exactly, yes, because in Keller paper it was denoted by D. This is a paper. It was denoted by this notation, but sometimes I found this W notation, and sometimes I use that. But here I was uh,
Because
following
in
in Keller.
functional analysis, we use W for Sobolev spaces.
In Malliavin calculus, people use this D.
And what is your delta K? What is delta capital K?
Yes, delta capital is a simplex. Let me. Yes, here it is. It is the set of T1, Tk in the
I
unit.
see.
Yes. Yeah,
Okay, thanks.
thank you.
Other questions, please?
Well, I have a question. So, did you try to move from Wiener space to more like complicated
Not yet. By the way, this is
distribution spaces?
yes. This is of course a very natural and good question. We still did not do this. By the way, this is still a work in progress. And of course, we plan to do much more than those particular examples. Yes.
Yeah, so it seems that like you need to some estimates on the density and property like convolution.
Certainly. Yes, certainly. Yes.
Yes.
Yeah.
Okay.
Okay, thanks.
Other question, please?
Can I ask question?
Yes.
I see that you approving convergence as measures for this kind of functionals. And so my question is it even possible for them not to be weakly compact? Do you have some interesting negative examples of that type? Or maybe they kind of always convert weakly compact.
Oh. Uh, one have to really look for this case. Yes, I don't have an answer for the moment. I don't have an
Okay,
answer for the
so
moment. Yes, but
so in this cases you consider it was always like this. Okay, thank you.
yeah, we considered examples where it is weakly compact and examples where we have even conversions. But it is of course very important to check if there are examples where there are no weak compactness. Yes, certainly.
Thank you.
Yeah.
Okay. Other questions, please?
I have one question. Could you
Please.
please repeat the motivation of finitely absolutely continuous?
Oh, yes. Uh, yes, I started from this example where you see that sometimes you have a measure with the square integrable density, and sometimes you have a measure which is associated to some positive generalized Wiener function. And in both cases, you have an orthogonal polynomial decomposition. That's exactly what finite absolute continuity can provide. It covers all these aspects. It fits very well to this kind of problems.
I see. Thanks.
Yeah, you're welcome.
Okay, next question, please. If not, let me also make just few comments. I must firstly to emphasize the importance of this self-intersection local times as a even geometric characteristic for processes which have non-smooth trajectories. It is well-known result. There exists well-known result of Legal related to the asymptotic of the area of the epsilon tube around the linear trajectory in two-dimensional case, and it occurs that despite or in comparison with the usual smooth curves or good sets in Euclid space, the area of epsilon tube contains a logarithm, powers of logarithm of epsilon, and coefficients are exactly renormalized at local times of self-intersection. But of course, this is only one example, and actually, the notion of the finite absolute continuity was introduced in order to cover the cases of positive generalized functional. Every Wiener positive generalized functional can be represented as from one side e to Wiener series, which converge in some negative space, and from other side, it can be represented by some measure which can be similar to initial measure. So it was interesting to have the description of all such measures which have e to Wiener analog of the e to Wiener expansion. And it occurs that such approach works. So for example, exactly about the fractional Brownian motion. It can be proved, it was mentioned also at the seminar before, that if we have a Gaussian process which is just Hölder in square mean of any order, Hölder of in square mean, one dimension, that it has a local time in this sense as a generalized function. So from this point of view, I think that we have a lot of perspective related to this approach, and hope that we with Naoufel will demonstrate some other achievements in this direction. Okay, for today we finish our job. And Katerina, who is the next speaker? Do you know?
Yes, the next speaker will be Georgy Ryabov.
Oh, okay. So we will again came back to stochastic flows. Okay.
Yes.
Surely. And for today, that's all. Thanks everybody for attention, and bye.